of advanced ordinary differential equations or advanced theory of ordinary differential equations. My name is Harishankar Mahato, and I'm an assistant professor in the Department of Mathematics at IIT Kharagpur. So basically, since you are all enrolled in this course, if you have looked at the syllabus, it must have given you an idea that we start from the point where I assume that you are already familiar with ordinary differential equations and some basic methods that we use to solve them. So anyways, I'm going to do a small introduction and I will give you a recapitulation of things that are related to first order and second order ODE, which you probably have studied in your graduation. And this course specifically deals with a little advanced version of it. So we'll look into the theorems like the first part of this course will be to look into existence of solution, extension of those solutions to the whole domain. Then we look into some stability analysis, then some part of the dynamical systems also we will cover. So as the course progresses, it will cover several things, and of course it is slightly theoretical, so I request all of you to bear with me, and if you have any questions or queries, then you can definitely ask me via email, or you can post in the forum. We'll be happy to answer. The teaching assistants will be also available to answer your queries there. All right, so we can start our first lecture. So let's begin. Also, I wanted to tell you something about the references. So the very first or classical book on this topic is the Ordinary Theory of Ordinary Differential Equation by Coddington and Levinson. So this is that book. It's a very classical book on theory of ODEs, and I recommend all of you to follow this book throughout this course, because mostly I will be following that book, and some other references that I have put in the syllabus. So for example, C. Constanda differential equation, then there is a separate book by Coddington on an introduction to ordinary differential equation. Then there is a book by Simons and Kranz on differential equations. So if you look at the course, the syllabus of the course, you will get to learn about all these references. All right. Okay, so let us begin. So today we will start with some basic introduction of ordinary differential equation. So first of all, just to give you a motivation, what is an ordinary differential equation? How do you motivate the concept? All right. So let us start with a very basic example. So consider. So we'll start with the very basic introduction of ordinary differential equation, and we'll see how we can motivate the idea of a differential equation. Okay. So consider a particle P with unit mass, right? That means the mass is 1, and denote basically t as the time, right? Yt as the vector of spatial coordinates. You can write it like this. You don't have to consider vector, it can be scalar also. Okay? Vector of spatial coordinates, or in plain words you can say the position of the particle, i.e. position of the particle, right? And y dot t represents the time derivative of y, right? That is, you may also call it as velocity. So basically rate of change of displacement is your velocity. So if we assume that we can force the particle to have a prescribed velocity v. So if we say that the particle has a prescribed velocity v ty, let us say, at any time t, then, and at the position y, then y dot equals to vty, right, y dot equals to vty will describe trajectories of such particles. Right. So if Vty is given as the velocity of the particle, then we know that rate of change of displacement equals to velocity. So we can write y dot equals to Vty. Y dot means dy dt equals to Vty. Now this particular equation, let us call it as equation 1, basically describes the trajectories or the path of all such particles which has this velocity, right. So this is a very basic introduction of your ordinary differential equation. So like an algebraic equation will involve powers of let us say x or y or whatever variable you are dealing with, so and equals to 0. So that is an algebraic equation. But when you are dealing with differential equation, it will basically involve the derivative of an unknown function with respect to the independent variable, right, and that derivatives, mixture of those derivatives, powers and all that must be equal to 0. So here you can see that our y, which is basically the unknown function or the displacement of the particle p, that's its derivative is written in terms of some function vty. So this is our ordinary differential equation, and if you look at the order of the derivative, then since it is a first order, then you call it as a first order ordinary differential equation. When you solve it, you will get basically the family of such trajectories which actually involves when you solve it, which involves a constant c. So for every value of c, you will get a different trajectory, and that c can be determined by using some conditions, right. So the very first order ordinary differential equation might look like this. Now not only first order, if you have, let us say, an ordinary differential equation where you have a power or when you have let us say square of this first order derivative, then what do we call it? So the similar type of problem, but suppose instead of having this first order derivative of that type, suppose you have an unknown function, but you have its square equals to some function f t y, right. So then in that case, this is a first order ODE, definitely a first order ODE. ODE means ordinary differential equation, but it is of degree 2, but it is of degree 2. So degree is basically the power of the highest occurring derivative. So if you have a, let us say, second order derivative and its degree is 1, and in the same equation if you have a first order derivative and its power is 2, but you can still call it as second order first degree, because you always look at the highest occurring derivative that is present in your differential equation, right. And if you talk about degree, then you look at the power of that highest occurring derivative term in your differential equation. All right. So this is our first example or first introduction of the first order ordinary differential equation. Now as I said, if you solve the equation 1, if you solve this equation, let us write in the scalar form itself. If you solve this equation, then you basically get something like y dot t equals to some c times some function of t, right, but where c will be any arbitrary constant. So you have to determine that c. So that means if you are looking at any particular particle p which is following this equation, you have to prescribe some kind of initial condition so that you can be able to determine that constant, and then you can say that if a particle starts from this particular point, then it will follow this trajectory, right. So in order to have a unique solution, you prescribe y at t0 is equals to some y0. Now this will give you a unique path that is followed by that particle p. So basically you have an ordinary differential equation, a first order ordinary differential equation together with some initial condition. So together these two are called as initial value problem, right. So we have first order ODE, we have initial condition, together they will be called as initial value problem. Alright. Now imagine, so you probably are aware of Newton's second law of motion. So if I follow Newton's second law of motion, and if I want to write down the equation of motion for the particle which experiences a force F, it experiences a force F, and if the displacement of the particle is denoted by yt, then we know all for a unit mass, we know that the equation of motion will be given by d square y by dt square equals to f, right. Alright. So this here is basically your second order ODE, because here the derivative order is 2. So you have basically second order time derivative of the displacement y. So this is a second order ODE first degree, right. So second order and first degree, or degree 1, that also you can call ODE, ordinary differential equation. Now comes the question, again if you are going to solve this equation, you must have solved these kind of equations, I am very certain. So when you solve these second order ODEs, you end up getting a solution which involves two arbitrary constants. Now for those two arbitrary constants, you will get different solutions all the time. If you are aiming to get the unique solution, again you have to prescribe some initial condition to the given ordinary differential equation. So let us say I am saying initially y at t0 is equals to y0 and dy dt at t0 is equals to some y10 or y1 simply, right. So in this case we will be able to determine a unique solution, and since you have here your let us say y at t0 and dy dt as at also t0. So this is again some initial conditions. So this is a second order, you can write second order ordinary differential equation plus initial conditions. So this is a second order ODE or second order ODE with initial condition, or we can call it as second order ODE or initial value problems. So basically we can call it as initial value problems, second order initial value problems, right. So depending upon the order and the degree of the given derivative of the unknown function, you can call it whether it is a second order, whether it is a first order, whether it is a first degree, second degree, and so on. It depends what kind of initial and initial conditions that you are prescribed, you will be able to determine the unique solution, right. So let us move on. Now in your ODE course, you have already learnt about different methods to solve an ODE, right. So I am going to just give you some recall of it, not the entire ODE that we are going to cover here, just some preliminary ideas. So suppose you are given a first order ODE, okay. So we have a first order ODE dy dx. Let us keep it a scalar case only, because it will be easier to make you understand. So, f of xy, dy dx equals to f of xy. So, the very first method that we used to solve it is the separation of variable, separation of variables, which means that if you have dy dx equals to y by x, so it is very simple, right? You can write it as dy by y and then dx by x, and then you integrate both sides. It will be log y, then that side is log x plus log c, and of course you can complement this equation with some initial conditions so that you can be able to determine your c, right. So, in this case we have by doing some minor multiplication here and there, you will be able to determine the solution, right. Separation of variable also works with an idea that the given ODE is actually exact, right. So, you must have heard also something called, so this is separation of variable, the second term that I am using is exact ODE, exact ordinary differential equation, exact ODEs. So, suppose your given ODE is of the form m dx plus n dy, right. You can put this ODE which is given like this into this form. You can just do the cross multiplication and then you will get your form as m dx plus n dy. Obviously, your m will be then in that case y, and n will be minus of x or something, right. Now, for this type of equation, if you have this form, then how do we write the exact form of this ODE? Exact in the sense that you should be able to write this equals to some d of psi in a way, and then psi equals to constant will be the solution, right. So, here also for this particular example, if I do some side calculation, I will have dy dx minus x dy, and then you can divide both sides by x square. So, this will become y dx minus x dy by x square, and this can be written as d of y by x, right. Now, you can integrate both sides and you will get y by x equals to some c, which is giving you y is equals to cx. So, you will get the same solution from here, you will get the same solution from here. The reason why we were able to write this as d of y by x, because it is following that exact condition in a way. So, here we will write the condition for exact solution, and then we will say that when it can be put into the form of d of something, right. So, the condition is we will not prove the theorem. The condition for checking the exactness is exactness condition will be exactness condition will be del m del y. I always check this formula. So, del m del y is equals to del n del x. If this happens, then this is the necessary and sufficient condition for the exactness, for checking the exactness of a given ordinary differential equation, right. So, for example, if I look into some formulas, so basically suppose if you have equation of this type, so one example could be, so I have some examples in my notes. So, I can write x dx plus y dy plus x dy minus y dx divided by x square plus y square, right. So, here in this case solving this equation is very straightforward, right. You just have to remember that whether you can be able to write it as a d of something. So, here this will become d of xy, d of x square by 2 plus d of y square by 2 plus d of tan inverse y by x equals to 0, right. Alright. So, here what do we get? D means you are basically doing d dx, but that dx is multiplied on the right hand side. So, 0 times dx will become 0. So, we are not writing d dx, we are just writing d, alright, but basically you are doing the derivative, just keep in mind. Now, if you write, then it will be d of x square by 2 plus y square by 2 plus tan inverse y by x equals to 0. You integrate both sides, that will be x square by 2 plus y square by 2 plus tan inverse y by x equals to some constant, and that is giving you the solution of this ordinary differential equation, right. So, as long as you can be able to write d of something, then basically your equation is exact, and you should be able to determine the solution, right. Now, let us see some more techniques that we have learnt over the time. So, of course, if your equation becomes exact, then there are several ways to find out the factor with which you can multiply. If the equation is not exact, then there are ways or the factors that you can use to multiply your given ODE so that it becomes an exact, right. So, this is what happens in this example. If you look at this example, so earlier it was not exact, but then I multiplied it by 1 by x square, and then it became an exact. So, if the given ODE is exact, then writing the solution is very straightforward. So, you can write d of that psi, so that function psi you can determine. But if it is not exact, then you basically do this multiplication. So, here we have that 1 by x square, we multiplied it and then it became exact and we wrote down the solution. Here we did not have to, because it is given to us that you can write first term as d of something, second term as d of something, and third term as d of something, and then it is exact. Alright. So, if it is not exact, you can make it exact by multiplying with some factors. Now, if you look into the your differential equations book, which you probably have studied in your graduation, there you will learn about how to determine these multiplicative factors. So, I am not getting into them, but the idea is that you have to multiply with it. Alright. Then you also have studied about something called integrating factors. So, integrating factors is again is used to make your left hand side right as d of something, right. So, basically what you have learnt is if you have an ordinary differential equation dy dx as px times y is equals to qx, then from here we wrote down the integrating factor as e to the power px px dx. Now, whatever you get from here, you multiply your equation with this integrating factor. Then your left hand side will become d of y e to the power integral px dx, whatever you get, and on the right hand side you will have qx, times e to the power integral px dx. Now, you integrate both sides with respect to x and you will get the answer. So, this method was also something that you have studied for solving a first order ODE, right. Then from first order ODE we move to second order ODE. The ODEs were of this type. Let us say a second order ODEs. So, we had this type of formula a0 y double dash x plus a1 y dash x plus a2 equals to 0. Of course, you supply some initial conditions to get the unique solution, but that is not important for the moment. Now, here a0, a1 and a2, they can be constants or they can be functions of x, right. Now, as long as they are constants, you can write the auxiliary equation, which you have already done before. So, you can write the auxiliary equation which is which is a0 m square plus a1 m plus a2 equals to 0. This will be obtained by taking y is equals to e to the power mx. This is our auxiliary equation. Now from here you can solve for m. M will give you two roots, m1 and m2, right? And then you can write down your solution, yx equals to c1 times e to the power m1x plus c2 times e to the power m2x. Alright. Now here I wrote down e to the power m1x, e to the power m2x because I assume that m1 and m2, they are not same and they are both real This formula will change when your m1 and m2 are same and when m1 and m2 are complex. That also I am guessing you already know. Alright. So this is the method to solve second order ODE. Now if you have a0, a1 and a2 as functions of x, then that falls under your Cauchy type, and then basically you have to make a substitution, and with the help of that substitution you again reduce it to a ordinary differential equation of constant coefficients, right. So that probably also you are aware of. Now on the right hand side, instead of 0, if you have, let us say, functions of x, then not only general solution, you also need to find out particular solution. Right now this is a general solution. For any C1 and C2, it will satisfy the given ODE. But if you have something on the right hand side, then you have to take if you have something on the right hand side, then basically what we will do, let us say you have a0 y double dash plus a1 y dash plus a2 y. I think I didn't write y in the previous slide. Let me just quickly check. Here it should be y also. This should be y. Okay. Now suppose if you have this type, a0 y double dash plus a1 y dash plus a2 y is equals to 0, and is equals to some function of x. So then in that case we will find a general solution by making the right hand side 0, and you use the auxiliary equation, and from there we write down the solution. And then we also find out the particular integral, which will be given by 1 by a0 d square plus a1 d plus a2 of f of x. And from here, because you can take y out, and then it will give you this a0 d square a1 d plus a2, where capital D is your d dx, and then you try to calculate this 1 by of this d operator of f of x. Clear? So for second order ODE, same technique can be used. If you have a third order ODE, you again take y is equals to e to the power mx as a general solution, and then you obtain the auxiliary equation. From there you write down the solution. You have to pay attention whether the roots are different, some of the roots are same, and some of the roots are complex. Then comes the question, what happens if the right hand side is non-homogeneous, whether you have functions of x. So if you have a functions of x, then you have to find out the particular integral also. So these are some common techniques that we have used for ordinary differential equation of higher order also. In this regard, I would also like to mention that there are some special type of ordinary differential equations which also involve some singularity that is present in the equation, and they lead to some very special type of functions. They are called as special functions, such as Lagrange polynomial, Legendre polynomial, Chebyshev polynomial, and all that. So those equations we solved by the method of series solution, right? That is not in the syllabus for the moment, but we did use series solution to solve ODEs with singularities in it. So there are a whole bunch of methods that we can discuss without discussing the theory, which has something to do with this course. So I tried to give you an overall idea of the methods and techniques that you have studied before. So from next class and onwards, we'll start from here actually. So with the assumption that you're already aware of these techniques, and how we can actually look into the theory part of this ordinary differential equations. First order, second order, doesn't matter, we'll just proceed from there. Alright, so I will stop here today, and thank you for your attention. We'll continue the discussion on existence of solution for ordinary differential equation in our next class.